Our next type of the chi-square test is the chi-square goodness of fit test. So as its name indicates, that it is comparison of observed frequencies to an expected predetermined model or ratio. It means that we are not assuming them to be homogeneous, or we are not assuming them to be the same in all categories. Rather, we are assuming that these frequencies, they should appear in a pattern, they should appear in a ratio. And we are going to check, we are going to test that whether our observed frequencies, they fit into that ratio or no. So what is the goodness of fit of our observed frequencies into those expected under that predefined ratio? And we are going to use the Mendelian ratios. For example, the law of independent assortment. So you remember that what is the phenotype ratio, what is the expected phenotype ratio? It is 9, 3, 3, 1. So this is the phenotype ratio for the law of independent assortment. So a farmer did a dihybrid cross of pea plants, and the plants were heterozygous for 2 traits. So these 2 plants, they were heterozygous for 2 traits, and he did the dihybrid cross of these pea plants. And these 2 traits were seed appearance and color. So this is the very famous example that every biologist, every biology student, that they study during their courses. So this is a very basic example of genetics, and you all must be familiar with these examples. So that is why I have taken this example. This is the example of law of independent assortment. So this farmer obtained a progeny of 556 seeds. Out of these 556 seeds, 315 were round yellow, 108 were round green, 101 were wrinkled yellow, and 32 were wrinkled green. So these were his results. Now the question is, does the result of this cross follow the Mendel's law of independent assortment? So this is the biological question, or this is the statistical problem that we have, that does the result of this cross follow the Mendel's law of independent assortment? The next step is to state the alternate hypothesis. Our null hypothesis. Our null hypothesis is the observed frequency distribution follows the Mendel's law of independent assortment. And our alternate hypothesis is the observed frequency deviates from the Mendel's law of independent assortment. So these are our hypotheses. The next step is calculation of expected frequency, and how we do calculate the expected frequency on the basis of our null hypothesis. So our null hypothesis is that this cross, the results of this cross, follow the Mendel's law of independent assortment. So therefore the phenotypic ratios should be 9, 3, 3, 1. So we calculate the expected frequencies on the basis of this model. So first of all, we calculate their ratios, we calculate their proportion values. So round yellow, 9 by 16. So what is the total of 9, 3, 3, 1? It is 16. So 9 by 16 is 0.5625. 3 by 16 is 0.1875. And 1 by 16 is 0.0625. And now we calculate the expected frequency. What is the total number of the progeny that the farmer had? These are 556. So 0.5625 out of the 556 should be the observed frequency for round yellow, which is 312.75. And for round green and wrinkled yellow, it is 104.25 each. And then for the wrinkled green, we have 34.75, and their total is 556. So this is how we calculate the expected frequency. So we are not considering them to be homogeneous, we are considering them to be following a predetermined ratio. And now the table for the calculation of the chi-square value. We have observed frequencies, we have expected frequencies, the total is same. So next step is the calculation of difference between observed and expected frequencies. The difference between the observed and expected frequency of round yellow seeds is 2.25. The difference between the observed and expected frequency of round green is 3.75. The difference between the observed and expected frequency of wrinkled yellow is 3.25. and the difference between the observed and expected frequency of wrinkled green is 2.75. And what is the next step? To take the square of these values, the difference between the observed and expected frequency of round yellow, the square of 2.25, and the square of 3.75, the difference between the observed and expected frequency of round green, then 3.25 square, the square of the difference between the observed and expected frequencies of wrinkled yellow, and then 2.75, which is the square of difference between the observed and expected frequencies of wrinkled green. Now we are going to divide this difference with the expected frequencies. So 5.0625, which is the square of the difference between observed and expected frequency of round yellow, is divided by the expected frequency of round yellow. And we have the value, which is 0.0162. So we do the same calculation for round green, for wrinkled yellow, and for wrinkled green. Now we take the sum of these individual values, 0.0162 plus 0.1349 plus 0.1013 plus 0.2176, and their sum is 0.47. So this is the value of the chi-square that we have. So what should be our next step? Next step is to define the degree of freedom and to compare this calculated value with the tabled value of chi-square. So our degree of freedom is, because there are 4 classes, so degree of freedom is 3. The table value that we took from the table of chi-square distribution is 7.815 at probability of 0.05. And as we can see that our calculated value is less than the table value at probability 0.05, so we are going to accept the null hypothesis. So the probability of null hypothesis to be true is greater than 0.05, therefore the results are non-significant. And therefore we are free to state that the result of cross follows the Mendel's law of independent assortment. The chi-square value is 0.47 and the probability of this value is greater than 0.05. So this is how we do the chi-square goodness of fit test. Then we have another example of the chi-square goodness of fit test, and this example is about the species composition of ground foraging birds, and 64% of the ground foraging birds in that area, they are sparrows, 29% are larks, and 7% are francolins. And these observations, they were made on the studies that were done in the past from that area, that 64% of the ground foraging birds are sparrows, 29% are larks, and 7% are francolins. So this is the frequency distribution that we have in that area. And then after 30 years, a new study was done to find out that if the species composition is same as previously found, or has it changed over the period of time. So 750 birds were observed, and out of those 750 birds, 495 were sparrows, 198 were larks, and 57 were francolins. So this was the species distribution in the new observation. Now the question is there any change in species composition, or is the species composition same as previously found, or it has changed? So this is the question that we are going to check. So again, we are dealing with the frequencies, so we have to apply the chi-square test. And what kind of chi-square test? The chi-square goodness of fit test, because we have a pre-existing ratio, the pre-existing relative frequencies of different nominal categories. So the next step is to state the null and alternate hypothesis. Our null hypothesis is there is no change in species composition of the area, and it is same as previously studied. And alternate hypothesis, obviously it assumes a difference, and it says that species composition is different from previous study. So these are our hypotheses. Next step is calculation of expected frequency under our null hypothesis, and this is how we do it. So sparrows, according to the previous study, they were 64% of all ground foraging birds, larks were 29%, and francolins were 7%. So this is how we calculate their proportions. That 64% means 64 out of 100, which is 0.64, and then 29 out of 100, which is 0.29, and 7 out of 100, which is 0.07. And the expected frequency in the 750 birds that were observed, the expected frequency is 0.64 into 750, which is 480 for sparrows, and 217.5 for larks, and 52.5 for francolins. So these are our expected frequencies. Now we have to apply the test. This is our chi-square calculation table, the observed frequencies and the expected frequencies, and you can see that their sum is similar. Then the difference between the observed and expected frequencies, it is 15 for sparrows, 19.5 for the larks, and 4.5 for francolins. Again, you have to ignore the minus value because we are going to take the square of this difference in the next column. So 15 square, which is the square of difference between observed and expected frequencies of sparrows, 19.5 square, which is the square of difference between the observed and expected frequency of larks, and 8.75 square, which is the square of difference between the observed and expected frequency of francolins. And what is our next column? Our next column is that this square of the difference between observed and expected frequency is to be divided by expected frequency of that class. So 225 is the square of difference between the observed and expected frequencies of sparrows, and it is divided by the expected frequency of sparrow, and we get 0.4688 value. And then we divide the square of difference between observed and expected frequencies of larks with the expected frequency of larks, and we get 1.7483. And then we divide the square of difference between the observed and expected frequencies of francolins, and we divide that by the expected frequency of francolins, and we get the value, which is 0.3857. Now we take the sum of these values, 0.4688, 1.7483, and 0.3857, and their sum is the value of our chi-square, which is 2.60. So this is our chi-square calculation. The next step is that we have to check that whether this chi-square value is significant or no. So degree of freedom in this case is 2 because there were 3 classes, so 3 minus 1 is 2. The table value that we checked from the chi-square distribution table is 5.991 at probability of 0.05 and degree of freedom 2. So which one is greater, our table value or our calculated value? Our calculated value is less than the tabled value. Therefore, we have to accept the null hypothesis. So probability of null hypothesis to be true is greater than 0.05, which means our results are non-significant. So there is no change in species composition, chi-square 2.62, and probability greater than 0.05. Or we can also say that species composition is same as previously found. The chi-square is 2.6 and the probability is greater than 0.05. So this is the example that how we can use the chi-square goodness of fit test to compare our observed and expected frequencies under some predetermined model or predetermined ratio. So this is the exercise that you have to do at home and share with me the results and discuss with me the results. And if you have any problems in solving this exercise, we'll discuss that in the question answer session. So example is the total number of weeds and quadrates collected from different fields. So these are 6 fields, and these are the number of weeds that are found in these fields. So the question is there a significant difference in the weed infestation among different fields? So we have the same observation, we have the same example with different observations, and the question is also same, is there a significant difference in the weed infestation among different fields? So you have to solve this problem and share the results with me, and you have to follow all the steps and then you have to come up with a proper result statement in the same format that I have provided you. And this is another exercise. In a dihybrid cross, a progeny of 3,839 seeds was obtained with following categories. So this is another example, and the question is, does the result of this cross follow the Mendel's law of independent assortment? So again, you have to state your hypothesis, you have to choose that what kind of statistical test you are going to use, and then you have to calculate your expected frequencies under your proposed null hypothesis, and then you have to calculate the chi-square value, compare it with the table value, and after you have done your comparison, then you have to state your results in a proper form. So this is all for this lecture, and in the next lecture we will discuss the other type of the chi-square test, which is the chi-square test of independence.